What kind of prediction score are you getting? So you can use score on a classification object. It's just not going to give you the explain variant score. It's just going to count the number of errors that have been made. But you can use score on one of these, and then you can tell me what kind of prediction error you're getting. Or not. I think we can do better. I'm not sure. So far this is really a simple example, nothing fancy. Just instantiate objects. We're going to fit and score in them. And we could vary the different parameters of the objects to try to improve the score. Does that make sense to everybody? I'm not going to do it right now because we're going to see how to do this in a clever way or efficient way. So I was getting a bit better than 0.9. I was getting 0.96 by using a simple k-nearest neighbor. Right? Should we move on? Any questions on linear models and what I've presented so far? No? So we're going to move on to support vector machines. So, unlike the linear models that I've presented so far, support vector machines are a discriminant model. They do not try to fit a probabilistic model. They just try to find the best way, given the train data, to discriminate observations. So just to let you know, right now I'm doing a bit of zoology of estimators, just to give you a feeling of what you can get. I'm not going to cover them all. This would be ridiculously boring. But I've taken a few examples just to show you the kind of stuff that we have and how to interpret them. So, if we look at the data, so we're described by two features and the 2D plane. So we've got on the one side, so that's a two-class problem. So on the one side we've got one class, on the other side we've got a second class. And what the support vector machine tries to do is to find a line that separates them. So slightly different than the linear models that I've shown before, because they were trying to minimize a residual. Here we're just trying to separate. And if we take a support vector machine without any regularization, it's just going to take all the samples. Basically, what it can be seen is take all the samples, do the mean of one class, do the mean of the other class, and use this as a vector to build a separating plane. This is what's done here. This doesn't work too well. What we would really want to do is to take the few samples that are close to the separating border and use these to build the separating hyperplane. So this is what's done here, so it's with regularization. Basically, the more regularization you have, the less samples you're going to take to build your separating hyperplanes. In jargon, machine learning jargon, these samples are called support vectors because they're the vectors. So a sample is a vector in a vector space, and they're the vectors that support the separating hyperplane. And the more regularization you put, the less support vectors you will have. So here we've put some regularization and it works much better. We've taken the few closest to the plane and we're using them to build a separating hyperplane. So support vector machines can be used either in regression, in which case they're called support vector regression, or classification. So we can try this on our iris data set. So we're going to import, this time we're going to import from SVM, support vector machines, rather than linear model. We can create a support vector classifier object. So it's svm.svc. And just for now, I'll put in kernel equals linear. We'll come back on this. And we can fit it to the trend data from the iris data set. Alright? So that's the way it goes. And then we can use the prediction on left out data. Or we can actually try scoring, for instance. Score. So we got 0.9 prediction. Just one caveat with SVMs. If you've got data with variance differing a lot in the different directions, SVMs are not going to work well. So it's the case for many estimators. You want your X data to be reasonably normalized, to have the same kind of variance on every direction. Elsewhere, you might force your estimator to consider more certain features, certain directions than others. Does that make sense? So we can look at the standard deviation of our data. So in each direction, it has similar standard deviation. If it was not the case, support vector machines wouldn't work well. Alright, now the real meat with SVMs is what's called kernels. So we've just seen a linear kernel. So with a linear kernel, we're trying to find a plane in observation space to separate observations. So here's the data set. This is an artificial one that I've created where the plane doesn't work. There is no way we can find a plane that separates this set of observations because there's this nasty one that lies on the other side. By the way, here I've circled in black the support vectors. So we've seen that it found a good compromise, but it cannot separate well. So this is a support vector classifier with kernel equals linear. So we can use a different kernel. We can use a polynomial kernel. So what it will do is that it will build the decision function as a polynomial of the distance, combination of polynomials of the distance between the support vectors. Right. So this is not obvious. What it does is, in a complicated optimization problem that I will not discuss, it selects a small number of support vectors and builds a polynomial with them. So here the polynomial is of order 3, sets the coefficient of this polynomial to find a decision function that maximizes the separation between the two classes on the training data. Does that make a bit of sense?
these methods, is there something that's like an ROC, like a plot that shows the probability of detection versus false alarm for these kinds of problems with this approach? Is that happening?
So, well, yeah, that's a very good question. So basically, you're asking, can we use ROC receiver operating curve to quantify the detection power? So yes and no. So first, we do have an ROC metric and area on the curve, for instance, in the Scikit. But for an ROC to be, so ROC, for those who don't know, is basically counting the number of false detection and so false alarms and true detections, varying a threshold. So if you accept everybody, you're going to do absolutely no false alarm, but a lot of false detection. If you refuse everybody, you're going to be doing a lot of, well, the other way around. But anyway, you're taking the compromise, you're varying the compromise, and you're looking at how well your estimator does. So this is actually a really interesting question, because SVMs are not a probabilistic model, so you don't really have an output probability. So you can't really vary thresholds. So you could be varying different parameters, but they're going to be ill-behaved. So if you try to plot an ROC curve with an SVM, most likely you're just going to get a jagged plot, because you're not really doing a threshold in the decision statistic. Though you can add probabilistic models to SVMs, and actually for a linear model we have, yeah, that's actually nice. So SVC has a predict proba. So basically, can be seen as in some way it can be seen as the posterior probability, except there is no probabilistic model. And then you could be doing you could be thresholding this one and doing an ROC on this. And just to point you to where you would be looking for ROC, there is a module called metrics, and in it you have ROC curve. But yeah, your question is pretty much how can I judge the performance, the prediction performance of my method. And ROC is going to work well for models that give me a continuous decision statistic only. So polynomial kernel, and another very, very useful kernel is the radial basis function kernel. So basically it's doing the decision function as a combination of Gaussians on each sample. So the decision function is going to look at, so not on each sample actually, on each support vector. So it's sticking, to get an intuition of it, you can see it as sticking a Gaussian kernel on all the support vectors, and on its positive weight on one class, negative weight on the other class, and the decision is going to be made by thresholding this. Right, so here's an example. So this is nice because it allows us to do a very complex decision landscapes. So if the classes are not linearly separable, which can happen in real data, you can, by using different kernels, there are more than this, you can create much more complex decision rules. Now, the danger is that you have much more parameters to learn. You're probably going to be putting much more Gaussian kernels when doing an RBF kernel. And so you're prone to overfit. And so each time it's a question of instantiating the support vector classifier with a different kernel. And the different kernels are parameterized with different parameters. For instance, the RBF kernel is parameterized with gamma, which is the size of the Gaussian. So if you have a tiny Gaussian, you're close to nearest neighbor. Does that make sense? If the size of my RBF is very small, then basically my decision rule is only affected by my nearest neighbor. If the size of my RBF is huge, then my Gaussian kernel is covering everything. And I'm going to be more like a linear model. On the one hand, I'm going to have a fairly flat, straight line decision function, and on the other hand, I'm just going to be looking at the closest. All right, so if you have the tutorial on your computer, you can download this file, svmgrind.py. So if you download it, and hopefully you can run it. Just run it in Python, not IPython. Can you run it? Does it pop up something like this? Right. So this represents the space of our two feature problem, and by clicking on it, we can add. You probably can't see. I can't blow the fonts here. You can add observations. So right click is going to create one class, left click is going to create another one. So I can just populate this space. And then below, you can fit an SVM to it. So you can press the fit function. So can you do that? Right clicks don't work. That might be an Apple problem. Which is a pity because there are lots of happens. Right, for those who can, because if you have only one class, it's
TKit?
yeah, it's a TK. But you know how to fix that.
You can help use the corner of the parent tab.
What's that?
You can help use the corner of the tab. That's the right one.
You can tell us you can what?
You go to preferences.
The corner.
Well, I think the problem is that the right click just does not work in the application. I think you know that right click. Oh, it does. Okay.
Yeah.
So how do you do that? Can you
If I control click, it works.
control click works?
Yeah.
All right, so you can just use control click. So the reason I'm bringing this up is this application up is that it's a great way to develop an intuition on how SVMs and kernels work. So here we have a linear kernel, and we can add data and see how it chooses support vectors to always have a small number of support vectors, but a good separating hyperplane. So you can see it adapt to new data that you put in, and we can see that if we add new data far from the margin, it's simply not gonna change at all its decision rule. But if we add new data that is close to the margin, it immediately adapts and will use this new data as support vectors. And we can see what happens if we start breaking the linear decision rule. So this is still linearly separable. This is not anymore. So you can just experiment a bit with the linear one, and then we're going to switch to an RBF one.
The dotted line.
The dotted line is the margin. So it's what it's trying to maximize. The SVM is actually trying to find a hyperplane so that it maximizes its distance to the support vectors. So this is why we say it's a discriminant model. There is no probability model. It's just trying to be as far as possible from its support vectors. Basically, the bigger this is, the better the model is. All right, so let's clear this and try again with a RBF kernel.
If you put the event button to 2 instead of 3, it works.
So we can see this as a break to see if it works also on Windows and Linux, and if so, then we can just change this. so we can just create classes, we can create observations. So now what I've done is I've switched to an RBF kernel. And so, darn, wrong button. That's fine. So I can create observations that are close to each other. And we can see that it's using its RBF kernel to pave the outer frontier of this small cloud of observation. If you can see this here, I've created a bunch of very clustered observations, and it's putting support vectors only at the outside of this, and the decision function, which is created by the RBF kernel on the support vector, just sits around it. And if I add the other class around, I'm going to be pushing the decision function in. We can also see that it tends to create a lot more support vectors than, for instance, the linear SVM, because it needs somewhat to cover all the observation with the kernel. So as I said, it's more prone to overfit. It needs to learn a lot of parameters. And chances are, if I shoot in a new observation in there, it is likely that if I can have a lot of observation during the training set, my decision function will be wrong. As usual, more complex model means more complex learning.
So if you got a new observation and it fit in that little convex region in the middle there, you would claim that it belongs to that category, right?
Yeah, it's the decision. So the decision is given by this back line here.
But if it's outside of that, it's the other class.
Right, absolutely.
All those other dotted lines don't mean it's the decision.
No, they're the margin, but they're really hard to understand with SVM, with a Gaussian kernel. So actually, this is really the decision potential. So we're seeing the zero isosurface of the decision potential, and then the 0.5 and the -5. And actually, if you wanted to do an RC curve, it might be interesting to vary the threshold of this decision potential. But you wouldn't be able to go at one end or the other end, because when you're far from the hybrid plane, it doesn't mean anything. It means something only when you're close from the hybrid plane.
Earlier in your other example with your visualization method, you were essentially editing out features that didn't help, right?
Yeah.
You're essentially zeroing out stuff. In this situation, because you're picking only a few members of that group to represent the support vector, is something similar is going on here, right?
It's the exact same thing. It's the exact same thing, except the thing is that the RBF kernel with so we could tune also the size. Here there's the gamma that we can change, but with this gamma, the RBF kernel does not cover a lot of the space. So we're closer to nearest neighbor rule, and we need a lot of support vectors to cover all the observations. Now, if we increase the gamma, didn't change anything. Darn. Oh yeah, it did. But no, we need to decrease the gamma. Gamma is the inverse distance. Okay, so I've decreased the gamma. So each RBF kernel is bigger. So now I have a much smoother decision rule. So I'm not sure why. I still have a lot of support vectors. So the way SVM works for multi-cloud problem is you do either, most often you do a one versus all. So basically, if I have three classes, each time I'm going to take one class and find the decision rule to separate this class from the two others. So that's three classification problems. And after this, given a new sample, I'm going to have a voting heuristic. Which of this decision rules does it score better? So that's called a one versus all problem. Another option is to learn a one versus one, as I'm going to take each pair of classes and fit a decision rule to this. And then once again, given new data, I'm going to have a voting heuristic. So this is in the Scikit-learn as a black box. So you don't actually have to understand how it works, but this is the way it works inside. No. Basically, so far, it depends on the underlying. So we're using, to be efficient, we're using, we try to rely on existing C libraries. And so depending on which C library you use, that uses either one versus all or one versus one. And it should be stated in documentation. In the long run, we'd like to expose this. Any other questions on this? So by the way, if we look at two classes of our iris dataset that I've shown here, these two are not linearly separable. Maybe you had noticed this earlier. Trying to fit lines to separate this data is not going to work. So we can try using SVMs to get a good prediction score. So these are classes 1 and 2 of the iris dataset. So we can try using SVM to get a good prediction score on this. So let's try this out. And just a hint, if you want to have a look at the decision function, well, there is a method on the SVM that is called decision function, and that given data will tell you the value of the decision function. So you can plot it on a grid to have the kind of plots I was showing and to allow you to get an intuition. So that's going to be our second exercise. So first difficulty to keep in mind is that the iris data set is sorted. So when you leave out data, either you need to permute the observations. So what I do is what I've done here is that I create a random order and I reorder my observation. Or you need some clever way of leaving out data. Elsewhere you're going to be leaving out only one class. And you're going to be totally biasing your estimate of your prediction accuracy. It's just one thing to keep in mind. Just looking at your y vector will tell you immediately whether you have this. Oh, another thing that I forgot to mention. I've purposely restricted the prediction to only the two first feature. The reason is it's hard to visualize a decision function in more than 2D. So just to get some visualization, even though that's going to kill our prediction power, let's do the prediction in 2D. So I've separated my data in a train and test set after shuffling it. So So just once again to shuffle, you don't want to shuffle separately your X and your Y, elsewhere you'd just be breaking the relationship that you're trying to learn. So the way I do this is I do a random permutation of the size of Y, and then I apply it to each of the data sets. And then I check that I have something that's reasonably evenly distributed. Then I just split. I take 80% in my training set, and the remaining 20% in my test set. Then I've just created a support vector classifier with an RBF kernel, because looking... Oh, and I forgot. Sorry, I said I was going to do this in 2D, but I forgot to do this. Oh no, I didn't forget to do this in 2D. So if I look at my data, so looking at your data, as Chris said this morning, is important, really important. And it's really hard when you've got high-dimensional data. So if I look at my data, nice. Right, I'm going to look at the solution, because I can't seem to plot that thing. Oh, there we go. Okay. Not sure what was happening. So if I look at my data here, clearly by looking at this data, I know, at least with this set of features, I'm not going to find a separating hyperplane. Just a straight line won't work. So looking at that, I would try to use an RBF kernel. Looking at that, we can also see that we're never going to get perfect prediction. There are some observations that are grouped, but some are lying out in the middle of others. There's no way with this amount of data I'm going to be able to learn a prediction rule that is going to work here. I need more data. Or I need more features. If I have a feature that separates the classes well, then it might work better. So anyhow, I'm still going to try. And I'm going to try it with an RBF kernel. And so then what I'm going to need to set is the size of the RBF kernel. So what I'm going to do is simply tune the size of the RBF kernel to maximize the score on left out data. So here I've created a support vector classifier with the RBF kernel. Then I can fit it and predict on left out data. And then I'm simply going to do this for varying gammas. I'm going to vary, I don't know, between -4, 10 to the -4 and 10 to the 2 with 10 values. And we can see that we can get up to 75 accuracy. And I can, so choose this. So that's the second to last one. So the gamma, the corresponding gamma is going to be 20, between 20 and 4, so I can take 10. So I'm going to set this as a parameter. I'm going to fit my data once again. Yeah. And then I'm going to plot the decision function, because I want to get an intuition of why it works or why it doesn't work. So I'm going to take a grid. And so looking at this, I'm going to take a grid going from, in the first direction, 1.5 to 4. In the second direction, 4.5 to 8.5. So we said 1.5 to 4. And in the second direction, 4.5 to 8.5. And just, not everybody knows this trick, but the NumPy.mGrid function can take a complex stride, which tells how much steps do I want. So this is basically a n-dimensional version of length space. So I'm going to create flattened versions of these things because my decision function. So my decision function, let's have a look at what its API is. So it really wants a 2D array as usual. So I'm just going to create flattened versions of these. And these are my observations. So now I need to make a 2D vector out of them. So these are going to be my test points for my decision function. So this is NumPy concatenation. Alright, so now I have a 2D vector with a 10,000 observation of dimension 2. So is everybody okay with the NumPy messing around without doing here? Created a grid. So that's described by two grids, a grid of x and a grid of y. Flattened them, stuck them together. Now I can look at the decision function on this grid. So that's test. So now I've got the decision value per test point. So I'm going to reshape it to have a 2D array. Then I can have a look at this, and I'm just going to do this in another figure so that I don't mess around. Okay, now I'm going to do the real thing. So I need to look at it and I need to overlay it with the existing data. So I'm going to use mshow, mshow, and the trick is just to set the extents. One way of doing this. Actually, this is not the way I've done it in the example, but that's fine. I think it's extent equal. And I want xx.min, yy.min. And then I want the point-to-point variability for x and peak to peak, sorry, not point-to-point. Great. So something like that. So something went wrong with my decision function. Alright, I'm going to look at my solution. I'm not sure what's wrong with what I did. Was anybody able to plot the decision function? No? Oh, well. I'm not going to fight with it because we can just run the example and get the result. It's probably some stupid mistake somewhere. So I'm just going to run the solution. Alright, you win. You win, thanks.
Where did the loading the solution, the link for the solution?
Link for the solution is,
Because that wasn't the mouse using that.
oh, correct. Looks like I made a typo in the, alright. Okay, I'm just going to edit real quick. Yeah, there's a typo here. Alright, if you refresh the page, it should be good. So is it working if you refresh the page? No, it's not. Hmm. Yeah. Hmm. Yeah. I didn't fix the problem.
This is you change the letters X. Is this size? Yes.
I need to push it. Alright, that should be good. So that's what we get at the end of the day for the 3 kernels. So linear is the easiest to understand, but it doesn't solve our problem. Polynomial is simpler. I haven't looked, I think that it probably works fairly well, but as we can see, it's still not able to separate. And RBF takes a compromise. That actually didn't work well at all here. So on this plot, the circled observations are the test observations. So the algorithm did not have them during the training. All right. Anyhow, this is not a good classification problem. We will not be able to solve it easily. I'm just bringing this out because this kind of stuff exists in real life, and it is. You simply cannot get good prediction on this kind of data set. You simply do not have enough information. Just have to live with it. All right. We're going to take a break. If there are any questions, just go ahead. And we'll be back in 1 hour.